Es geht jetzt weiter hier mit den Vorträgen und zwar darf ich begrüßen Thomas Telkamp, Papa Alpha 8 Zulu. Herzlich willkommen. Und der Vortrag lautet Dwingeloo Radioteleskop. Und ja, it's your microphone.
Okay. Thank you. Good afternoon, everybody. Apologize, I have to present this in English. My German is not good enough to do a full presentation. I understand it very well, but speaking is another challenge. When you walked in here, you already have seen the 20-meter dish. We're going to talk now about a 25-meter dish, very similar in size. And you will see there are a lot of common things we do with these dishes. And I want to explore a little bit further what we can do in the future. So, yeah, there we go. Let me see this. Yeah. So this is the Dwingeloo dish as it is today. On the back, in the back there, you see the Radio Astronomy Institute of the Netherlands. That is the owner of the dish. The field over there you see is a LOFAR test field. And this is the Dwingeloo dish itself, right nicely on the side of a nature reserve, which means that to the south we don't have much radio interference because nothing will be built there. Well, that was actually the theory when they built it in 1955. Now we see LTE towers in the south, but still there is a little bit of space. So let's start in the beginning. The telescope was inaugurated in 1956 by Queen Juliana of the Netherlands over here. And on the left, this is a picture we only recently found in an archive where you see the building of the telescope. And there's a lot of interesting things in here. For example, there's a railroad we had never seen before. This is a kind of stand where they have made the mirror on when they were building it. The mirror is still fixed with two cables. And maybe the most interesting part here, there's a horse with a car behind it. So this is the time when the telescope was built. Many discoveries have been made with it since that time. It was the first fully steerable radio telescope in the world, built for that purpose. It was also the biggest telescope in the world for a while, until Jodrell Bank was built. It was specifically built for mapping the Milky Way, so with the hydrogen line, but all other discoveries have been made, like high velocity clouds, recombination lines, even two complete galaxies have been discovered with this instrument, and a lot of surveys have been done. The beam is roughly the size of the moon, so it takes a lot of time to make a complete map of the sky, and that is what this telescope has been doing in its later years. This is the interior of the telescope when it was built. Everything running on vacuum tubes, of course. Apparently it was extremely warm in here all the time. That's also one in all the pictures you see the window open and the jackets off, because it must have been terribly hot in here. None of this equipment is currently available. This has all been replaced in the years later, of course, by more modern equipment. The telescope has been used until 1998, and then it was just parked and nothing was done. Now, you see what happens if you don't maintain a telescope that is outside. I mean, here you have a nice dome over it. You need to replace the domes once in a while, but here this thing is outside. It starts deteriorating. But luckily, in 2007, a group of volunteers, mostly radio amateurs, basically have restored the telescope into function. They managed to actually get it moving again within a year or so, but after a while it proved that there was bigger maintenance needed. So in 2012 they took it down for 2 years to do actually complete refurbishment of the whole system. So here you see them taking off the dish itself, which has been completely reconstructed. Which means that now we actually have a very nice, fully operational telescope that we can use for all kinds of purposes. So this is how it looks today. So the telescope is owned by Astron, which is the Radio Astronomy Institute. They also pay for the big maintenance, like the painting or cleaning of the dish. The operations of the dish is done by a foundation called CAMRAS, or the Dwingeloo Radioteleskop Foundation. This is part of the volunteers, several radio amateurs in there. You might recognize some people. And with this group, we basically keep the whole dish operational. There are very different skills in here. Some people with an astronomy background, a lot of people with a mechanical background, just keeping this thing moving, the oil pumps, everything. It takes a lot of different skills and a big team to make this work, but together we do this, and we still use it to do new projects and new discoveries. So on the radio amateur side, you might recognize Jan van Melwijk, who is doing most of the EME work. I bet several people of you have worked him. Who is doing a project here together with Heinbach, who is a German audio artist, and they're bouncing voices off the moon, and he's recording them for a project. So the dish is used a lot by radio amateurs for EME work. I'm not going to talk about that a whole lot, because that's very clear what they do and how that works. The other big reason we have this foundation is outreach. So in the summer, every Sunday we do tours, and we explain what radio astronomy is, what the dish is, how it works, and we have a whole team of volunteers who give these tours. It's really nice to do, because you get a group of people who don't know what radio exactly is, they don't know what radio astronomy is, and you have 45 minutes to give them an impression of why this is important. Why do we need radio telescopes if we already have optical telescopes? So it's a really eye-opener for a lot of people. This is the most amazing demo we have. With this telescope, we can live listen to a pulsar. So when a sun, like ours, or actually a little bit heavier than ours, when the fusion pressure cannot withstand the gravity anymore, it collapses. For very big stars, it becomes a black hole, but for intermediate stars, it becomes what they call a neutron star. So the star, which is like 1 or 2 million kilometers diameter, collapses to a sphere of just 10 kilometers. But all the angular momentum it had remained in that sphere. So you get a small sphere that is rotating very fast. Over the years, they slow down. And if we tune to that, or actually if we point to that pulsar and we put an AM demodulation on it, you get this. So you hear, sorry, yes, thank you. You hear the pulses live coming in, and basically this is a radio station, 3,500 light years away from here. So these pulses you just heard live have basically been transmitted when the Egyptians were building the pyramids over here. And now you can live receive them. It's like, I don't want to call it a QSO, but it's the ultimate connection you can make. This is really, if you're ever in the neighborhood of Dwingeloo, come visit us. This is a life-changing event if you can actually hear this. So that also brings me to another part of the setup. It's the software setup. So we have an SDR connected to this telescope. So all this old equipment we don't use anymore. We basically just have an antenna, LNA, and it directly goes into the SDR. And then we have a set of tools that split the IQ that comes out of the SDR in various streams, so we can do multiple things in parallel. So for example, when this pulsar demo runs, at the same time, actually it's animated, yeah, other tools are doing pulsar recording. So we have a huge data set now, which you can actually even detect the motion of the Earth in for over a year, which is just collected by all the people who give the tours without even knowing it. So we can run multiple tools on the same stream. And I'll come back to that because that's an important aspect of how we operate. Another thing we can do with this telescope, and this is one of my personal favorites, is to take papers that have been written, discoveries that have been made with this telescope. So here we have a paper from 1966 about hydrogen recombination lines. I don't have the time to go into that, but basically it's ionized gas which is emitting radio waves. And it emits a line, basically, a signal, every 25 megahertz or so. So whatever band you're in, you can receive these things. So they did that in 1966, and we can repeat that with our SDR setup in 2025. So what took them probably months to do is like an afternoon these days with the SDR. So the telescope is basically better than it has ever been. These are very weak signals. So to give an impression, this peak you see here is 0.01 dB high. So it's a really weak signal. We will be talking about Voyager later. Voyager is extremely strong compared to these kind of signals. But we can do it, and we can repeat these papers and actually compare the results to what they have done before. So we do a lot of other stuff, and in the 30 minutes I have here, I cannot cover everything. We do moon landings, well, exactly like Peter already presented, and I think we will later hear about the Japanese landers. The telescope actually is a SatNOx station, so we can schedule a pass, and then the full telescope will actually track the LEO satellite, which is really fun to do, because the telescope will move really fast. Even if the satellite is over 40 degrees or so, we will not be able to track it. The telescope is just not fast enough to follow the LEO. But it's really useful because we can receive satellites that have antenna problems. So if the antenna doesn't deploy, we can still receive it, and we can gather data for them. So we help especially university teams with field antennas doing that. Other things on the radio astronomy side are high OH measures. And this one is interesting. This is fast radio burst. This is basically flashes of radio that come from somewhere in the galaxy or outside of our galaxy. And we don't know exactly what it is. They don't repeat. Sometimes they repeat, sometimes they don't. So these are very rare events, and we actually captured one of them. But these were the things I was not going to discuss. So back to the software side. What we use is a set of tools we have written and developed ourselves, and basically it's VRT, Vita radio transport, over 0MQ. So what we do is we create a stream, a 0MQ stream, and in this stream we multiplex the data itself at a very high data rate, like 20 megasamples, and we put in the context. So every 100 milliseconds or so, you get a frame that says, well, I'm tuned to this frequency, this is the sample rate, this is the gain. So you have a lot of data in that stream that describes the stream. What we also put in that stream is even more metadata on the telescope itself. So we have the pointing in there, the tracking. So if you have the tools that use this data, you get your IQ data, you get your information about the sample rate and everything, and you get information about the telescope. So you can build tools that do something with all this data, and again, you can have multiple tools using the same data source. So we support multiple SDRs. The most important one is the ATES one, and then we have various tools that can use them. So we can, for example, put it in GNU Radio. We have some GUIs for our demos that we have. We can write it to file, where we use the SIGMF format. You can just look at the spectrum, or you can run tools like specific tool sets for Pulsar. But again, the thing is you can do this in parallel. It's not one tool that claims the SDR and that's it. You can do a lot of things at the same time. So here's a more extensive list. A very interesting one is STRF, which is a tool from Case Bassa that is used by a lot of satellite people to create the TLEs after launches. So you can actually run this in parallel to any observation that we do. This is a very useful one called VRT Spectrum. It simply creates a spectrum from the IQ stream, and it does that in a format that you can see here. It's just a CSV file. So you can run this for 10 minutes, open it in Excel, and anybody can do something with it. And this is basically what we use for a lot of things. So if you just put the dish somewhere in the sky and you leave this tool running for a day, you get a map of the Milky Way, basically. It's really that easy. I think this one was even made with, no, this one was done with the telescope, but you can do this with a 1 meter dish as well. So just 2 commands. You start the daemon for the SDR, you run the tool to collect the data, and you open it in your favorite program to process it. So I did a similar thing. I just pointed at QO100 for a few days, collect the spectrum, and you can very nicely see the utilization of the wideband transponder. I have the same data for the narrowband transponder, and it's also, now you can just count the yellow lines, and you can calculate the percentage of the transponder that is in use. So a very nice way to just keep track of the transponder. And again, it's just 2 commands, and you get a file that you basically can make a picture of like this. So it's all for convenience. Of course, we have these nice tools, and we will hear from the gentleman over there, that you also want to use. So we made a plugin for both SetDump and SDR++ that connects to the stream. So you just start SetDump, you press play, it will automatically find out what you're tuned to and what the stream is, and it will show it. And then you have all these nice decoders that you will be telling about later. So now we get to the first project we actually do with these tools. And should it? Oh, no. This should be animated. I think I put the wrong slide in it. Okay, it's not animated. This was a really nice animation of the launch of Voyager, and you would see it come out of the plane. It's not an animation, right, Jens? Oh, it is. Yeah, can you start it? Yeah. Almost, yes. Oh, that was it. It only starts up. Yeah, there we go. So, this is the launch of Voyager 1 and 2 in 1977, and you see their voyage through the solar system. So you nicely see the direction changes at the planets. There's Voyager 1. Now it speeds up, otherwise it takes ages. And you see it go out of the plane, out of the ecliptic. And you get an idea about the distance. And this basically is where it's now. So of course, this is the ultimate reception of a signal that was man-made. So we really wanted to do this, and this has been done, of course, here by AMSAT in Bochum in 2006 already, a long time ago. But we had never done this because this is our feet in Dwingeloo. And by default, we have 70 centimeters with the cross dipoles, and we have 21 or 23 centimeters with the feet you see there in the middle. If we want to do X-band, we actually have to go up to the front end and put that 3 centimeter feet in there. But as you see, it sits inside the 23 centimeter feet. So we can only do this for special projects. Then we install it, we do our project, and then we remove it again. There is a 13 centimeter feet on the side. That still works, but if you put the 3 centimeter on the side, you're too far out of focus, so that will not work. So we only did this like a year ago for the first time. And well, of course, we tested on stereo A, like here, and then we can receive all these deep space probes. So the way we do this, we have a nice lift, which comes out of the ground. So if you park the dish in a certain position, you can go up and you can do some maintenance on the front end. You can easily take the complete front end out and take it down with you, and you can do your maintenance on the ground, and then you bring it up. We can do this within an hour. We can do a major change on the front end, so that's quite good. So here again, this is the setup. So we have the SDR. Here's the tool that creates the stream. We also inject the tracking. So we track Voyager, but we put the tracking inside the streams, and we create 2 streams from it. One goes to a channelizer that is tracking. So basically the channelizer de-dopplers the signal for the known speed of Voyager. The other one doesn't de-doppler, and it just saves the IQ, because you always want to have the raw data. You don't want to have modified data. And then on the right here, we put VRT spectrum on GNU plot, and then you see the live signal, and the other one is being saved to file. And this is basically what we got. So this is a plot of 10 kilohertz of spectrum in 1 hertz bins. So you see we have roughly 4 dB carrier to noise in 1 hertz of signal. So this was a big achievement for us, many years after what you have done in Bochum, of course. So we gave all the credits for the first amateur detection of Voyager to here. But still, yeah, this is amazing. And it's actually only until this morning I realized again how special it is to receive these things. I mean, this is so far away. Because we have these tools, we can easily run a carrier tracker with it. So when the measurements are running, we also log the frequency of the peak. And we just do that for the whole day, and after the day you get a nice set of points. You compare it to what is in horizons, and you see that we have a perfect fit with the Voyager trajectory. Now yesterday I had asked Peter and Jens here if I can plug in the SDR, so I brought one from home, just into, over here, into the S-band, the X-band down converter feed. To do another experiment. Actually, Voyager was not on my list, but then yesterday afternoon, I think Peter suggested, like, we can look at Voyager. So I have the whole setup that I have a Dwingeloo also running on my laptop. So here we go, 2006. Some of the people you might still recognize. And there we go to yesterday, and there it is again. So here you have the peak from 2006, and there you have the peak from yesterday. In all these years, Voyager has traveled a lot of distance, so the signal is really weaker at this point than it was years ago. This is really diminishing it. It's 25 billion kilometers away today. So this was the exact distance at the time of the capture over there. So this was really nice to do. Right now, the dish is tracking Voyager, and the peak is visible here in the room next door. So this is being done live right now as well. Good. I need to look at the time and move to the next project, which is also a form of moonbounce. So of course, the radio amateurs do that a lot. So all the equipment is there. We have nice amplifiers. We can switch between receive and transmit. So we can do it for other experiments as well. So again, we have the same set of tools, but now we also have a tool to send, so we can play SIGMF files. So for example, we make a file with a carrier, we press play, and it will send it to the telescope. Now we do this together with the telescope in Stockard, which is another 25-meter dish, which can receive at L-band, so we do this in the 23 centimeter band. We transmit, Stockard receives, and we get 3 files back. 1 from Dwingeloo, 2 from Stockard, because Stockard has 2 polarizations that we can receive. And we can do interesting things with these transmissions. Oh yeah, that was the moon. You can do the same on Venus, of course. So this is the setup. I'm not going to cover that in a lot of detail. So let's see what happens. So this is 6 seconds of data, IQ data. Here we transmit a CW. Because we receive also our transmitted signal, you get a huge overload of all the LNAs and the ADCs, etc. So all these lines you see here are basically just images and our overload. You also see that we switch the relays just before we start transmitting and after we transmit to prevent our receiver from being, or actually prevent the LNAs from being burned. This is really critical. If we make one mistake here, the whole telescope is gone, RF-wise, but that's a known problem. So we transmit, and then we see very nicely here at the expected time, we see the signal coming back. A little bit of Doppler shift, and you see a bit of fading. The signal is sometimes faded out, which is, I think, known very well to the EMEers. Now, there's much more we can do. So this is what they did in the 60s. If you send a pulse to the moon, you see the various reflections from various parts of the moon, not just from the front. So the first reflection is the one at the top, and then you see later reflections, which have a much broader Doppler because of the apparent movement of the moon. With this, you can actually make maps of the moon, and that was our goal here. So we do the same trick, but instead of sending a CW, we're sending now a structured signal, which is called, in our case, a Zadov-2 sequence. When we do that and we look at the return, we can see very nicely the peak of the signal being returned at the front of the moon, but you also see echoes from much later in time, which are basically echoes from deeper on the moon. So further on the moon away, because we see half of the moon, so the sides are much further away than the front of the moon. So now we can actually see where the reflection is coming from, and if we combine that with doing that in frequency, we can start making maps. I'm going to skip this one as well. This is the sequence we use. It looks like chirps, but they aren't. It's a different type of sequence. But basically, this transmission you compress into a single point, and with that, we get a picture like this. So this is just a single transmission between Dwingeloo and Stockard of 60 seconds. This is done with only 70 watts of power, which is not a whole lot. And you already see the first craters showing up on the moon. Now, this we can, of course, improve. The interesting thing is we transmit an RHCP, which is standard for EME on 23 centimeters. We can receive in Stockard both LHCP and RHCP. And you see that with the LHCP, which is the one you expect, because it mirrors on the moon, RHCP becomes LHCP, you have a lot of signal, it's very strong, but the other one, you get more detail. So the craters basically reflect in another way than the main sphere does. So this gives a lot of information to build these kind of maps. And this is basically the best we got so far. And again, I have them in 2 polarizations. This is many transmissions overlaid. And you see if I switch between them, that one of them has more detail and the other one has more power. But this is what you can do with basically amateur equipment on 2 big dishes. Now this is very tricky to get to a map, because that's the ultimate goal, because the northern hemisphere and the southern hemisphere of the moon are overlaid because of the Doppler. I think this is animated. In a complicated way. So the next step in this project is to actually make these pictures at different view angles of the moon, such that we can separate these images. That's the goal. Here's one I like a lot, so I want to show it. This is basically the echoes on a shorter time scale. So the picture you saw was like a full minute. Here you see 4 seconds, and you see that different parts of the moon start having constructive and destructive interference. So basically you see where on the moon the signal is being reflected. So this is real time. This is basically 30 seconds that you replay in real time, and you see where on the moon your reflection is coming from, and you see it move around. And this is basically the fading you experience when you're doing your EME connection. But I think this is one of the first times to actually visualize it real time. Good. The next one, as you can see, is Venus, because it's very close to the sun when it's close by. So this was last year when we wanted to try bouncing a signal of Venus. In some way it looks like we're repeating everything you have done here, but at some point we'll do something new. Same setup, which again I will skip. So here we had to place a bigger amplifier, because with 70 watts on 23 centimeters we're not going to bounce a signal of Venus. We could calculate that. So we had a 1 kilowatt transmitter that we borrowed, but we also wanted to put it in the front end, so we don't have the cable anymore from the ground to the front end. So here we are on the elevator. This is the complete front end. Over here you see the 1 kilowatt amplifier, and here we're pushing it back in. This is again Jan van Melwijk, who some of you might know. So we had a whole plan. We would start with sending CWs, and then we would send these interesting sequences so we could map Venus. As you can already see, the first 4 were successful and the rest failed, unfortunately. So we only had the signals, only had the CWs. So this is basically our current control room. You see some old equipment, but actually most of it is the new stuff, and here you see the SDR again. I'm doing this here together with Tamerjan Dijkema and Kees Basse. And here we have the results. This was our Venus bounce for the first time. So we had 4 transmissions, and we have a reception each time at Dwingeloo and a reception in Stockholm. Especially the Stockholm receptions are really good. I think it has to do in Dwingeloo that we were heating up in the front end a lot because of the 1 kilowatt transmitter. So there the signal actually was much lower. But if we aggregate all of it, we get to a full detection of both telescopes of 10 sigmas, which is a really, really strong signal back from Venus. So, and this was at 23 centimeters with 1000 watts. Here we do a similar thing, but now we look at the frequency offset as well as the frequency rate offset. And this actually is a good way to prove that what you're seeing really is Venus and not some kind of RFI or coincidence in another signal. As I said, only the 4 first CWs succeeded. After that, the complete amplifier melted down. I think it basically desoldered itself. There was no cooling at all. It was inside the front end, which is a metal box. We could have foreseen this, but we only had 1 chance. So yeah, why not? And it has been repaired. It was only a few transistors, and we donated those transistors back to the one who loaned us the amplifier. Very good. So now we come to yesterday again. So I hooked up the SDR, and I could not I wanted to do the test with 2 telescopes. But I could not use Dwingeloo, because putting an X-band feed in Dwingeloo is something that requires a team to do. You cannot do that on your own. So I used my home dish, which is 1.5 meters, and I pointed it at stereo A, and we pointed at stereo A here in Bochum. Now, it's so strong that even on a 1.5 meter dish you have a clear signal. And I wanted to make a recording on both sides exactly at the same time with the same settings. So I see stereo A in 2 places, but with a different Doppler, because we're in different places on the Earth. if we see the accuracy, if we compare the SPICE model of the stereo A orbit together with what we measure, we see that Bochum is tracking very accurately. The same at my home. There's a little bit of an offset of a few hundred hertz, but that's just the oscillator of stereo A. If we look at the difference between the two, so we see 280 hertz difference between the two sides, we're also tracking that accurately, only we're measuring here in 1 hertz interval, so we cannot really get to more detail if we do it this way. This was just a quick check that the whole setup was working. What I really wanted to do, and this was just the first test, and I did it yesterday, so I didn't have the time to really process it, is to do interferometry. Basically, we want to measure the phase between the two signals on a very short time scale, and we do that by multiplying them. If we multiply them, you start seeing that you actually have a strong fringe, and if we track it, the phase, we see there's a bit of variation. So this is, remember, this is 3 centimeter band, 3.5 centimeter band. So there's a little bit of movement from plus 3.5 to, let's say, minus 10 centimeters. So we're basically accurately tracking here the position of stereo A to centimeter level, to 10 centimeter level, which in itself is already amazing. The big question is where the clock drift is coming from, because it's not linear. So one of our clocks was not fully stable. And I don't think it was mine, but let's, we need to dive into that. No, this was really a first test. It can be all kinds of issues. We need to figure out how to make this more stable. But even this, I mean, we're doing interferometry at 8.4 gigahertz, which is already an achievement in itself. Okay, and that actually brings me to the points I wanted to make for today. So there are so many things in common, and we already work together. I mean, we exchange a lot of information on moon landings, like frequencies. If we get information from one of the companies, we share it with each other. That already is really useful, but there's so much more we can do together, I think. To begin with, there's no astronomy on this side, as far as I know. Now, you have higher frequencies, so it's more difficult to do things. But also this site is called the Sterrenwarte. So it would be interesting to do something on astronomy here as well. I mean, you have the dish, you can do it. We should also really look at joint measurements. I think we do very nice things on ourselves, as seen with the moon landings, but we can do something with an interferometer. We could actually see if that's something we can do for Artemis. And these radar things, we can also do at 13 centimeters. So we can also do this between Dwingeloo and Stockert. And with S-band, we get more detailed maps of the moon because of the wavelength is shorter. Of course, we can work together on software. I mean, you already have AMSAT-DL, and actually we have the whole setup, AMSAT-DL setup basically copied from what you do here. And some of the tools we have might be useful for you as well. On outreach as well, I mean, we both want to reach an audience, and there might be things we can share there and cooperate on. And we should have a look on what we're going to do with the Venus bounce. We might do it again, maybe on 23 centimeters. Getting a 13 centimeter amplifier is more difficult for us. But definitely we should make a plan here with multiple telescopes to see how to handle this. That's it. Then I have one more thing. If you're really bored with your telescope, this is something that Tamoyan made. It's just a small script. And I have to say that it says light, not 8. Everybody thinks it says 8, but that's Okay. Thank you.
Okay. Yeah, thank you. And any question here in this room? There? Just a moment, please. Use the microphone, please.
Thank you very much. How much antenna gain do you have in Dwingeloo?
We have 49 dBi on 23 centimeters. The other thing which is interesting is that we compared the G over T on X-band with Bochum, and we have exactly the same G over T. So the dish here is smaller, but it's a solid dish. We have a mesh dish, so some of the 10 gigahertz or 8 gigahertz is going through it. So we have the same performance on X-band. And the numbers for 13 centimeter, I don't know from the top of my head.
Okay. Another question? Okay.
Yep.
Just wait for the microphone.
You have shown the different feeds basically.
Yes.
In the beginning, actually, how critical is the feed position, especially on the lower bands or on higher bands, actually, because you don't want to change feeds all the
No,
time.
this is the real issue. So the main purpose of the telescope is 70 centimeter and 23 centimeter. So those get the center. Anything else needs to be on the side or a one-time thing. So 13 centimeters on the side, but that gives you about 1.5 to 2 dB loss because you're out of center. For higher frequencies, it gets more. So X-band you cannot do on the out of the center anymore. So that's why we put it temporarily in the middle then, but then you block the other feed. That's basically it. I think 7 millimeters. Yeah.
Okay, thank you. Another question? No. Yes, then I will try it. Herrlich bedankt for your Lezing, tot ziens. Thank you.